Welcome to one of the strangest phenomena in quantum mechanics, the Quantum Zeno Paradox, where watching a quantum system can literally freeze its evolution. Imagine a quantum system that should naturally evolve and change over time, but if we keep measuring it, something remarkable happens. The system appears to freeze in place. Let's start by understanding what this paradox actually is, and why it's so strange. This effect is named after Zeno of Elea, who proposed several paradoxes about motion and change. The most famous is the arrow paradox. Zeno argued that at every instant of time, an arrow in flight occupies a specific position and is therefore motionless. If it's motionless at every instant, how can it move? Similarly, in quantum mechanics, if we measure a system frequently enough, we can prevent it from changing its quantum state. Each measurement causes the quantum state to collapse, resetting the evolution process back to the beginning. Now let's look at the mathematics that describes this phenomenon. Let's consider the simplest quantum system, a two-level system, like a spin that can be up or down. Initially, our system starts in state 0, which we write using this bracket notation called a ket. Under normal conditions, the system evolves according to the Schrödinger equation. The state at time t is given by this exponential operator acting on the initial state, where h is the Hamiltonian energy operator. For very small time intervals, we can approximate this exponential using a Taylor expansion. This gives us the state after a small time delta t, which is approximately the original state, plus a small correction proportional to delta t. Let's calculate the probability that our system transitions to a different state. We want to know the probability of finding the system in state 1 after some time. This probability is the squared amplitude of the state 1 component in our evolved state. For short time intervals, something interesting happens. The probability grows as the square of time. The transition probability is approximately proportional to delta t squared, where h01 is the matrix element coupling the two states. Here's a graph showing how the transition probability grows quadratically with time for short intervals. This quadratic dependence is crucial for understanding the Zeno effect. Now let's see what happens when we make repeated measurements. Imagine we want to evolve our system for a total time t, but we divide this time into n equal intervals. Each interval has duration, delta t equals t divided by n. After each small time interval, we perform a measurement to check if the system is still in state 0. The probability of staying in state 0 after one interval is 1 minus the transition probability. This equals approximately 1 minus the transition probability, which we can write as 1 minus a constant divided by n squared. After n consecutive measurements, the probability that we never observe a transition is. The total probability is this quantity raised to the nth power, since we need to stay in state 0 at every measurement. Now comes the crucial step. What happens as we make more and more measurements? Let's examine what happens when n becomes very large, meaning we measure more and more frequently. This limit equals 1. This is the key mathematical result. As we measure more frequently, the probability of remaining in the initial state approaches certainty. This graph shows how the survival probability increases as we increase the number of measurements. With frequent enough measurements, the system essentially freezes. You might be wondering, why does measuring more frequently prevent the system from evolving? It seems counterintuitive. The answer lies in quantum measurement theory. Each measurement collapses the wave function back to a definite state, and evolution must restart from there. Let's work through a specific numerical example to make this concrete. Consider a spin-half particle in a magnetic field with specific parameters. Let's say the coupling energy is 10 to the minus 15 joules, and we want to evolve for 1 second. First, let's calculate what happens with no measurements. Wait. This gives a nonsensical result greater than 1. This means our approximation breaks down, and the system definitely transitions. Now let's try with 100 measurements during that 1 second. Each interval is 0.01 seconds. Again, our approximation shows the system will transition in each interval. Let's try with 10,000 measurements, so delta t is very small. Now with delta t equals 10 to the minus 4 seconds, the probability of staying in state 0 after each interval is about 90%. But raised to the 10,000th power, this still gives essentially zero. We need even more measurements. Let's revisit the paint drying analogy to build intuition, while acknowledging its limitations. Imagine watching paint dry. If you stare at it constantly, checking every instant, it seems to never finish drying. Of course, this is just an illusion with paint, but with quantum systems, the effect is real. The analogy breaks because paint actually does dry regardless of observation. But quantum systems genuinely behave differently when measured. The analogy is useful because it captures the idea that frequent checking somehow interferes with a natural process. Has the Quantum Zeno effect actually been observed in experiments? Absolutely yes. The Quantum Zeno effect was first experimentally verified in 1977 using trapped ions. Researchers trapped individual ions and used laser beams to both measure and manipulate their quantum states. By adjusting the frequency of measurements, they could control the rate of evolution. Modern experiments use superconducting qubits, which are tiny circuits that behave quantum mechanically. The Zeno effect has practical applications in quantum computing, where it can be used to protect quantum information from errors. Interestingly, there's also an opposite phenomenon called the anti-Zeno effect. Under certain conditions, frequent measurements can actually accelerate the decay or transition, rather than preventing it. This graph shows how the decay rate can initially increase with measurement frequency in the anti-Zeno regime, before eventually decreasing in the Zeno regime. Whether you get Zeno or anti-Zeno depends on the detailed spectral properties of your quantum system and how the measurements couple to it. The Zeno effect touches on one of the deepest mysteries in quantum mechanics, the measurement problem. A fundamental question: what exactly counts as a measurement that collapses the wave function? Where exactly does the quantum system end and the measurement apparatus begin? This boundary is surprisingly unclear in quantum theory. Some interpretations even suggest consciousness might play a role in collapse, though this remains highly controversial. The Zeno effect doesn't resolve the measurement problem, but it dramatically highlights how strange quantum measurement really is. Beyond philosophical puzzles, the Zeno effect has real practical implications. In quantum computing, we can use the Zeno effect to protect quantum information by frequently checking certain properties without destroying the quantum state. This represents a quantum memory where frequent monitoring of error syndromes can freeze the evolution of errors, protecting the stored quantum information. We can stabilize fragile quantum states that would otherwise quickly decay or decohere. In principle, the Zeno effect could be used to control the outcome of chemical reactions by selectively freezing certain quantum pathways. Let's look more carefully at what happens mathematically during a measurement. In quantum mechanics, a measurement that checks if the system is in state zero is described by a projection operator. This projection operator is written as ket 0 times bra 0, and it projects any state onto the state 0 component. After we measure and find the system in state 0, the state becomes. The new state is the projected state divided by its norm for proper normalization. This projection operation effectively removes all the evolution that occurred since the last measurement, resetting the system. You might wonder, is information lost when we measure and the wave function collapses? Yes, information about the quantum superposition is irreversibly lost. This is one reason measurement is so special in quantum mechanics. The Zeno effect depends critically on the relationship between timescales and energy scales. Every quantum system has a characteristic timescale for evolution. This timescale tau is Planck's constant divided by the characteristic energy E of the system. For the Zeno effect to work, we need to measure on a timescale much shorter than tau. The measurement interval, delta t, must be much less than the natural evolution time tau. This graph shows that we need to measure on a timescale much shorter than the natural evolution time tau to see the Zeno effect. The Zeno effect is intimately connected to the energy-time uncertainty principle. The energy-time uncertainty relation states that the product of energy uncertainty and time uncertainty must be at least h bar over 2. When we make very frequent measurements, we're looking at the system on a very short timescale delta t. According to the uncertainty principle, this requires a correspondingly large energy uncertainty. This large energy uncertainty means we can't distinguish between states with small energy differences, which is why transitions appear frozen. What happens in more complex systems with many energy levels? The Zeno effect isn't limited to simple two-level systems. It works for complex systems with many energy levels. This energy level diagram shows a multi-level system. Transitions between any pair of levels can be frozen by frequent measurements. An interesting question: can we selectively freeze some transitions while allowing others? Yes, by carefully designing what we measure and how often, we can selectively inhibit certain transitions while permitting others. It's essential to distinguish the Zeno effect from another quantum phenomenon called decoherence. The Zeno effect involves controlled, deliberate measurements, while decoherence is uncontrolled interaction with the environment. Decoherence occurs when a quantum system interacts uncontrollably with its environment, destroying quantum coherence. The Zeno effect, on the other hand, uses controlled projective measurements that we deliberately apply. Both phenomena can suppress quantum evolution, but the underlying mechanisms are fundamentally different. What happens if we monitor a quantum system continuously, instead of with discrete measurements? Continuous quantum measurement is described by stochastic differential equations that include random noise. The evolution includes both the normal Hamiltonian evolution and additional measurement-induced terms. This creates individual quantum trajectories that differ from run to run due to measurement randomness. These jagged lines represent different quantum trajectories under continuous measurement. Each run gives a different random path, but all tend to stay near the initial state. The Zeno effect raises deep philosophical questions about the nature of reality and observation. If frequent observation can prevent change, does this mean observation somehow creates or determines reality? The Zeno effect exemplifies the observer effect in quantum mechanics. The act of observation fundamentally changes what is being observed. The Zeno effect challenges simple deterministic views of nature, showing that the act of measurement plays an active role in dynamics. Some philosophers have even connected quantum measurement to debates about free will and consciousness, though these connections remain speculative. The Zeno effect isn't unlimited. There are practical constraints and challenges. Every measurement requires energy. We can't perform infinitely many measurements with finite resources. The energy per measurement times the number of measurements must be less than the available energy. Real measurements take a finite amount of time. We can't measure instantaneously. The measurement apparatus has finite bandwidth, limiting how quickly we can extract information. Strong measurements can have destructive back action on the system, potentially destroying what we're trying to preserve. Current research is exploring new frontiers of the Zeno effect. Researchers are developing quantum logic gates based on the Zeno effect that can be more robust than conventional gates. There is speculation that Zeno-like dynamics might play a role in biological processes like photosynthesis or avian navigation. Combining Zeno effects with topological quantum states could provide even stronger protection for quantum information. This represents a topological quantum computing architecture where Zeno measurements could enhance the already robust topological protection. Let's summarize the key points about the Quantum Zeno Paradox. First, frequent quantum measurements can effectively freeze a system's evolution, preventing transitions between quantum states. Second, the effect arises because transition probability grows quadratically with time for short intervals. Third, the Zeno effect has been experimentally verified in various quantum systems, including trapped ions and superconducting qubits, confirming its reality and importance in quantum mechanics.